Hi everyone, my name is Inga Kindstedt, and today I'm going to be talking a little bit about firn warming in response to atmospheric temperatures at Eclipse Icefield. Eclipse Icefield is an ice field that's located in the St. Elias Mountains, marked by the yellow star here. The St. Elias sit right on the border of Alaska and Yukon, and also at the intersection of the traditional territories of several First Nations, including the Kluane White River and Champagne and Ijack. Now, the St. Elias Mountains are one little blob of mountains, but they're part of this much longer chain of mountain ranges that runs all up and down the coast of the Gulf of Alaska. And having all of these mountains right next to a large body of water means that these coastal ranges just get hammered by snowfall. And that, in turn, means that this part of the world is a really great one for growing glaciers. So all of the blue that you see in the map here, those are all glaciers. Um, Last year at Borns, I talked about Eclipse. And really what I focused on was the results from some field work that a bunch of CCI grad students went and did in 2023. One of the things that we did was we went up and we drilled firn cores. So firn is a big focus of mine, and really all firn is old snow. It's snow that has made it through at least one melt season, and it's on its way to being compressed into glacier ice. And so we went up to Eclipse and we drilled 3 cores down into the firn to look at the layers that were there. And what we found, the big takeaway was that there are all these features, and these are largely features that are associated with melt. So there's a bunch of melting. Eclipse is not dry. That was one big takeaway. Another was that the firn at Eclipse is actually quite warm. At parts in areas of the ice field, firn below 10 meters depth is less than 2 degrees Celsius from supporting liquid water, from being at the melting point. And I use 10 meters depth as kind of a benchmark here because that's often the depth that's cited as the typical penetration of the annual temperature wave. So firn below that should be insulated enough from what's going on at the surface that changes in surface temperature behavior aren't really felt. So with this in mind, I went ahead and decided to model the firn at Eclipse to think about, okay, well, this is what it looks like now, but what might it look like in the coming decade given observed trends in atmospheric temperatures? And the tool that I used was the Community Firn Model, or CFM. The CFM is a an open source model. It's coded in Python and it's modular. So it has the base firn densification module, which models the densification of snow into firn. And then it has a bunch of optional additional modules. And so I used the meltwater module. The things that I put into the CFM are an accumulation rate. So I used a mean annual accumulation rate that's based on measurements at Eclipse. Surface temperature, which to get surface temperature, I used weather station data from a weather station that is about 30 kilometers from Eclipse. Weather stations measure air temperature. So what I did is first I corrected that weather station data for the difference in elevation between Divide, where it's located, and Eclipse, where I'm interested in. And then I used those air temperatures to calculate surface temperatures, which went into the CFM. And then I also fed the CFM a surface density value, and I used a whole range of values uh, based on measured surface densities across the St. Elias because we don't have a good grasp on what surface densities are at Eclipse specifically. And then I tested it to see which values within that range would produce realistic outputs at Eclipse. So those are all the things that I fed into the model, and then the CFM spit out for temperature, density, and liquid water content over time. When I run the CFM, I think of it running in 3 phases. So the first phase is the spin up from 1983 to 2013. The second phase is from 2013 to 2023, where I am trying to reproduce observations that have been made at Eclipse. And then the third phase is from 2023 to 2033. And this is where I move away from reproducing observations and into projecting what might happen. So thinking about that here, these are some results. This is surface temperature. So this is surface temperature at Eclipse from 2013 to 2033, with that first half being where I'm feeding temperature data that's based on measured air temperatures. And so we're trying to reproduce what we've seen at Eclipse. And that second half being where we're trying to project what's going to happen in the next 10 years. Um, This is 50 replicate model runs. So 50 times I ran the model with the same settings, and they all produce the same temperatures from 2013 to 2023, excuse me, because that's where we're basing it on those weather station measurements. Then from 2023 to 2033, that's where we don't have measurements. And so what I'm doing is I'm looking at temperature distributions from those 10 years where we have data and then randomly pulling values for each day of year for the 10 years in the future to produce like a synthetic temperature record. And then because I'm a very visual person, to try to wrap my head around what's happening in 2033, I plotted up the distribution of surface temperatures. So that was for the surface. I can do the same thing for 5 meters depth. And so what I'm seeing here is that, okay, the amplitude of our annual cycle has decreased greatly, which is what we'd expect given the insulating effect of the overlying snow and firn. Um, but we're still getting up to the melting point in the summers. At 10 meters depth, uh, this effect is even more amplified, where we see smoothing out of the cycles. We still see reaching up to 0 degrees Celsius in the summer. Same with 15 and 20 meters depth. The thing that jumps out to me here is, well, we see this nice smoothing of the annual cycles, which we'd expect because of the insulating effects of snow and firn. And we also see that even at 20 meters depth, we're still getting some model runs where we're getting temperate firn, which is not the case at Eclipse right now. Um, but it makes me think that maybe Eclipse is at a transition point or near some threshold. So for this next section, I focus on 15 meters depth. All of these model runs that I've shown you here are all run under the assumption that the climate is not changing. Those synthetic climate records going up through 2033, those are assuming no change in current climate. Now I'm going to focus on 15 meters depth because it's below that 10-meter threshold. And I'm going to run the model with a variety of different climate scenarios. So this is the same thing we already saw. We're looking at 15 meters depth here. This is assuming a continuation of current climate through 2033. If I cool or warm the air temperatures by 0.1 degrees Celsius, um, things don't look that different. But if we look at the distributions in 2033 of those 15-meter depth temperatures, it seems like, okay, well, maybe we're a little bit more skewed toward colder temperatures with the cooling scenario, and maybe we're a little more skewed toward or warmer temperatures with the atmospheric warming scenario. Let's bump up that warming to 0.2 degrees Celsius, and we're definitely getting more of a skew toward higher temperatures at 15 meters depth. Um, Even more so with a half a degree of warming, and certainly with a full degree of warming. It seems like many of our model runs are producing temperate firn at 15 meters depth. But let's quantify that. How likely is firn at 15 meters depth to be at 0 degrees Celsius year round by 2033? And I focus on year round here because that is what would allow the sustenance of liquid water in the firn through the wintertime. So looking at that 0.1 degrees Celsius cooling scenario, none of those 50 model runs produce temperate firn year round by 2033. 2% of the model runs produce temperate firn year round by 2033 uh, with a continuation of current climate and with 0.1 degrees Celsius warming. That bumps up to 12% with a 0.2 degrees Celsius warming, about 50% with a half a degree, and almost all of the model runs produce temperate firn year round in 2033 with a full degree of warming. So a couple things I take away from this. One is that firn conditions even below 10 meters depth are sensitive to air temperature. The only thing I'm changing here is air temperature. And the other thing I take away is that, wow, it does appear that firn temperatures behave in a threshold way. So again, those takeaways from our field work were that Eclipse is not dry and that parts of the ice field are less than 2 degrees Celsius from supporting liquid water. And then my modeling work here has added to that firn conditions even below 10 meters depth are sensitive to air temperature and that we can reasonably expect to see threshold behavior at Eclipse. And with that, I would just like to thank the coring team, the folks I worked with on the modeling, and all of our supporters. Thanks so much.